simplest shape, a uniform thin rod of mass m and length L. Case 1. Axis passing through the center, perpendicular to the rod. Using integration, we get I equals ml squared divided by 12. Watch how it rotates about point mass m at distance r from the axis. The moment of inertia is simply I equals mr squared. It's that simple. Mass times the square of the distance. But for extended bodies made of many particles, we need to add up contributions from each particle. I equals the sum of mi times ri squared. And for continuous bodies, this sum becomes an integral. I equals the integral of r squared dm. This integral is how we derive. Before we begin, let me share some powerful tricks that will help you master this topic. Here's an amazing memory trick I call the ring, disc, sphere, rule of halves. Look at these three shapes: ring, disc, and solid sphere. For a ring, the moment of inertia is mr squared. For a disc, it's half of that, 1/2 mr squared. And for a solid sphere, it's 2/5 mr squared. Notice how the coefficients keep decreasing as mass gets distributed closer to the axis. Here's a key insight you must never forget. Moment of inertia depends on three things. 1. The mass distribution of the body. 2. The axis of rotation. And 3. How far the mass is from that axis. Watch this rod carefully. When we rotate it about its center, the MOI is ml squared divided by 12. But the same rod, rotated about its end, has MOI equal to ml squared divided by 3. That's 4 times larger. Same rod, different axis, completely different moment of inertia. Remember this. Now let's understand what moment of inertia really means. In linear motion, we have mass. In rotational motion, the equivalent quantity is moment of inertia. Think of it this way. Just as mass tells us how hard it is to change an object's linear velocity, moment of inertia tells us how hard it is to change an object's rotational velocity. Look at this beautiful analogy. F equals ma becomes tau equals I alpha. P equals mv becomes L equals I omega. Kinetic energy 1/2 mv squared becomes 1/2 I omega squared. Mass m corresponds to moment of inertia I. This is why we call moment of inertia the rotational mass. Let's define it precisely. Moment of inertia is a measure of an object's resistance to changes in its rotational motion. Watch these two wheels. The heavy wheel with more mass takes longer to speed up and slow down. The light wheel responds quickly to the same torque. Higher moment of inertia means harder to rotate. Lower moment of inertia means easier to rotate. The factors affecting moment of inertia are: 1. Total mass of the body. More mass means more inertia. 2. Distribution of mass. Mass further from the axis means more inertia. 3. Position of the rotation axis. Different axis means different inertia. For a point mass m at distance r from the axis, the moment of inertia is simply I equals mr squared. It's that simple. Mass times the square of the distance. But for extended bodies made of many particles, we need to add up contributions from each particle. I equals the sum of mi times ri squared. And for continuous bodies, this sum becomes an integral. I equals the integral of r squared dm. This integral is how we derive.
Welcome to MAGPIEHUB, your trusted partner for JEE and NEET physics solutions. Today, we're diving deep into one of the most important topics in rotational mechanics: moment of inertia of uniform bodies with simple geometrical shapes. I have all our formulas. The SI unit of moment of inertia is
kilogram/meter squared. Let's start with the simplest shape, a uniform thin rod of mass m and length L. Case 1. Axis passing through the center, perpendicular to the rod. Using integration, we get I equals ml squared divided by 12. Watch how it rotates about its center. Case 2. Axis passing through one end, perpendicular to the rod. Now the formula becomes I equals ml squared divided by 3. Notice that the end axis, MOI, is exactly 4 times the center axis, MOI. This makes sense because more mass is farther from the axis when rotating about the end. Next, the circular ring or hoop of mass m and radius r. Here's the beautiful thing about a ring. All the mass is at the same distance r from the center. This makes our calculation incredibly simple. The integral becomes I equals r squared times the integral of dm, which equals mr squared. I equals mr squared. This is the simplest and largest coefficient, just 1. About a diameter, using the perpendicular axis theorem, we get I equals mr squared divided by 2. Now the uniform circular disk of mass m and radius r. A disk is like many thin rings stacked together. To find its MOI, we integrate over all these rings. We take an elemental ring at radius r with thickness dr. Its mass is dm equals the surface density times 2 pi r dr. Its contribution to MOI is di equals r squared dm. Integrating from 0 to r, we get I equals mr squared divided by 2. Notice this is exactly half of the ring's MOI. Why? Because in a disk, mass is distributed from center to edge. Some mass is closer to the axis, reducing the overall MOI. About a diameter, I equals mr squared divided by 4. The solid sphere of mass m and radius r. A solid sphere distributes mass in 3 dimensions, so even more mass is close to the axis compared to a disk. This means the moment of inertia will be less than that of a disk. About any diameter, I equals 2/5 mr squared. Remember this, 2 over 5 for a solid sphere. Let's compare the coefficients. Ring, 1, disk, 1/2, solid sphere, 2/5. The trend is clear. As mass gets distributed closer to the axis, MOI decreases. The hollow sphere or spherical shell of mass m and radius r. In a hollow sphere, all the mass sits on the surface at radius r. Unlike the solid sphere, where mass is distributed throughout the volume, here, all mass is at maximum distance from the center. About any diameter, I equals 2/3 mr squared. Remember, 2 over 3 for a hollow sphere. 2/3 is greater than 2/5, confirming that hollow bodies have higher moment of inertia than solid bodies of the same mass and radius. The uniform solid cylinder of mass m, radius r, and length L. The cylinder has 2 important axes to consider. About the central longitudinal axis, I equals mr squared divided by 2. Notice, this is exactly the same as a disk. The length doesn't matter for this axis because each cross-section is a disk. About an axis perpendicular to the length through the center, I equals m times r squared over 4 plus L squared over 12. This formula combines contributions from both the radius and the length. For a hollow cylinder or tube about its central axis, I equals mr squared, same as a ring. The uniform rectangular plate of mass m with sides A and B. This is a planar body, perfect for applying the perpendicular axis theorem. About an axis through center, parallel to side B, I equals ma squared divided by 12. About an axis through center, parallel to side A, I equals mb squared divided by 12. About an axis perpendicular to the plate through center. Using the perpendicular axis theorem, I equals m times a squared plus b squared, all divided by 12. This is simply the sum of the other two. Now let's learn the powerful parallel axis theorem. This theorem relates the MOI about any axis to the MOI about a parallel axis through the center of mass. I equals ICM plus md squared, where ICM is the moment of inertia about the center of mass axis, m is the total mass, and d is the distance between the two parallel axes. This theorem is incredibly useful. If you know the MOI about the center of mass, you can find it about any parallel axis. Example, rod about its end. I end equals ml squared over 12 plus m times l over 2 squared, which gives us ml squared divided by 3, exactly what we derived earlier. The perpendicular axis theorem, but with an important condition. This theorem applies only to planar, that is, two-dimensional, bodies. For a planar body in the xy plane, Iz equals Ix plus Iy. The moment of inertia about an axis perpendicular to the plane equals the sum of moments of inertia about any two perpendicular axes in the plane, all passing through the same point. Example, circular ring. We know Iz about the central axis equals mr squared. By symmetry, Ix equals Iy. So mr squared equals Ix plus Ix equals 2Ix. Therefore, Ix equals mr squared over 2, the MOI about a diameter. Let's quickly review all the formulas. Thin rod about center, ml squared over 12. Thin rod about end, ml squared over 3. Circular ring, mr squared. Circular disc, mr squared over 2. Solid sphere, 2/5 mr squared. Hollow sphere, 2/3 mr squared. Solid cylinder about axis, mr squared over 2. Hollow cylinder about axis, mr squared. Quick memory aid for the coefficient order. Ring is 1. Disk is 1/2. Hollow sphere is 2/3. Solid sphere is 2/5. As mass concentrates toward the axis, the coefficient decreases. Now, here are some crucial exam tips specifically for JEE and NEET. Tip 1. Memorize the coefficients, not the full formulas. 1, 1/2, 2/3, 2/5. These fractions are the key. Tip 2. Always check which axis is specified in the question. The same body with a different axis gives completely different answers. Tip 3. Use the theorems to derive, not memorize. The parallel and perpendicular axis theorems can help you derive formulas you've forgotten. Tip 4. For complex shapes, break them into simpler parts. Calculate MOI of each part and add or subtract appropriately. Tip 5. Remember, hollow bodies always have higher moment of inertia than solid bodies of the same